my colleagues Eric and Soren are here with me, and if there are questions that they can easily address when they appear on the chat window, they will address that right away. If not, we will address those questions at the end of this presentation. So, yeah, without further ado, I hope everyone can see my screen. And to give you a short summary of what we will be covering in this 60-minute webinar, this will cover about a little introduction about scatter, also about leakage, and what limits are there in scatter and leakage measurements, and how to conduct leakage and scatter measurements, as well as introducing a possible efficient method and leakage and scatter measurements that you can adapt in doing these measurements in your facilities. So, as I mentioned, we will have a Q&A if time permits at the end of this presentation. Before we proceed to the actual content of our presentation, let me just give you a brief introduction about the RTI Group. So the RTI Group was founded in 1981, and it was a result of a thesis project at Göteborg Technical University in Chalmers, Sweden. And in that same year, in 1981, the RTI introduced the first non-invasive KVP meter to the market. If some of you might be familiar, that first non-invasive KVP meter is called the DTX. And over many years, there are new RTI products that have seen the light of day, and we have prided ourselves for the efficiency and reliability of our X-ray QA solutions. So what you can see here is the three offices of RTI. Our headquarters is located in Mölndal, Sweden, and we have two satellite offices. One is in the US, in New Jersey, and another one is here in Singapore, where I am located. So, as Dr. Nukuma mentioned earlier, joining us at this webinar to help us with the Q&A later is our product manager, Soren, and our training manager, Eric. So, as I mentioned earlier, this is a photo just to share with all of you of the first non-invasive multimeter in the market, which is called the GX. And you can notice from this photo that we have improved so much over the years on what is available for us with this type of X-ray multimeters. And so later on, we have more compact models coming along. So what you can see here is the Mini X and the PMX series, followed by this Solidos. And for many years, these were the state-of-the-art multimeters in the market. So I think you will not be surprised if we still see some of these instruments in some of the QA kits in the medical physics department in different hospitals around the world. So as use of the solid state X-ray meters grew, the demand for more versatile instruments appeared as well. And as a result, RTI has introduced what you might know, what some of you might know as the Barracuda. And this could measure up to 8 parameters or values simultaneously from this platform. We have this red Piranha, which is a more compact and versatile meter, which is an improvement of the Barracuda. So now from this red Piranha, we have also introduced a more improved version, which is now what we call the Black Piranha. And on this, you can on this slide, you can see the different Piranha models, and the Piranha multimeters are designed for multimodality X-ray QA. But then, if you are interested more on single modality QA, we also have the Cobia family, and together with our Ocean software, we offer a more efficient QA solution, and also to address specific measurement needs for different modalities. We have what we call the probes that can attach to either the cobia or the piranha multimeters, such as dose probes, CT probes, ion chambers, light probes, and MAS meters. And as we have mentioned on our invitation for this webinar, we also have this new probe recently launched in RSNA 2020 for scatter and leakage measurements, and simply called the scatter probe. So, as many of you are aware, these are all solutions for X-ray QA. So let's just move into what is X-ray QA, and where does RTI belong in this QA sector. So I just would like to take a minute here to explain what we mean when we talk about X-ray QA. So here are the different medical X-ray QA applications. So what we have here on one side is the diagnostic field, wherein you have all these different imaging modalities, and this is mostly where our solutions are intended for. However, there is also this section in the therapy application, wherein there is the use of the image-guided radiotherapy, and that portion wherein the kilovoltage energy is used, we can also, our instruments from RPI can also be used to do QA. So, and one of the elements of the QA testing, both for the diagnostic area and this therapy area, is the testing for leakage and scatter. So let's just go a bit more into detail about what is leakage and what is scatter, and we'll do that one topic at a time. Let us then start with leakage, and let's start to take a closer look into leakage. Okay, so some of you, or actually I would say probably many of you, are very familiar with these topics already, but then, okay, let me probably go through you with this as a review. So the leakage arises because, as you know, for X-ray production, here in the tube, we have X-ray emitting in all directions from the target or the anode, and not just in the direction of the primary beam. So although this tube housing is shielded, heavily shielded, I might say, some leakage radiation can still be transmitted. So that's one of the things that we are interested to measure and make sure that this leakage radiation is within permissible limits. So what are the limits of leakage radiation? So if we look into the Cohen standards, there are usually two that we use this as reference. We have mostly, I would say, all around the world, we refer to the IEC standards, but there is also the FDA standards that we are familiar with. And if we just look into these two standards, the similarities, I would say, is that the leakage radiation should be measured from 1 meter from the source, from the focal spot of the tube, and it should be measured over a 100 square centimeter area. So what looks different in these two standards are the units of measurement, wherein the FDA requirements are given in 100 millirentgen in 1 hour, and the IEC standard is given in 1 milligray in 1 hour. There's also this standard that is given for accessible surfaces, and this is measured at 5 centimeters from accessible surface. Same for FDA and the IEC. And then um, for the area of measurement, that differs from the two standards wherein the IEC mentions 10 square centimeter and the FDA mentions 100 square centimeter. Also, for the limits, IEC requires 20 microgray in 1 hour, and is saying 2 millirentgen or 18 microgray in 1 hour. So if you will notice here, this is not right. The statement or the requirement mentions in 1 hour. And what does that mean? So that means that we have to normalize these measurements based on the workload. And there is some computation required when we do this leakage measurements. So we need to normalize our measurements based on the power rating and maximum kVp of the machine. We have to refer to the set MAS and typical MAS consumption. There's leakage technique factors that are provided by the manufacturer, but then again, there are exposure settings which are recommended by the different regulatory bodies depending which country you are from, and then you use that to do your leakage evaluations. Okay, so now let us move into scatter. So what is scatter? So scatter radiation is a result of the coherent and incoherent scattering process in diagnostic radiology. So this scatter radiation arises from an exposure of an object which is along the path of the primary beam. So that could be most of the time, of course, a patient. But then, for purposes of QA testing, we usually would use a phantom. So there are factors that affect this amount of scatter, and one is the volume of the object being irradiated. So some of you might be familiar, if you have a bigger patient, then you have a bigger scatter. And if you have a smaller patient, you have a lower scatter. And the spectrum of the primary beam, as well as the field size used, are also two factors that affect the amount of scatter produced from an exposure. So the fluence and the quality of this scatter radiation have angular dependence, and it doesn't have the same intensity in all directions. So, and when we look into the procedure in measuring scatter, that will make sense on why we are saying that on this, the fluence and the quality of this scatter radiation have an angular dependence. So we'll go back to that concept later. So this scatter radiation normally is of a special concern in fluoroscopy procedures, because for those of you who might have seen how this fluoroscopy machines are used for vascular or surgery procedure, you normally would have different people standing here next to the table. You have the doctor, you have the nurses, you have the anesthesiologist, and radiation technologist. So those kind of environments is heavy concern in measuring scatter radiation. So on a normal exposure, both the scatter and the leakage are generated. Thus, this two type of unwanted radiation are an area of concern. And from a radiation protection and safety point of view, it might affect adjacent areas to the X-ray rooms. And to ensure that safe operations, radiation limits have been decided, and they're actually similar in many markets. So if we just take a look at these limits, the limits are divided into two categories. Let's first take a look at the occupational exposure. So the occupational exposure limits are for people who have some training in radiation safety and are normally monitored for radiation exposure. For some of you who are in this webinar, you know that for people like you working in hospitals, you are wearing what is called the personal dosimeter, or the badge, which could be a TOD or an OSL detector. So these people who falls under the occupational exposure limit have better control over accumulated exposure. Now, if you look into public, these are people who are visiting patients or just passing close to an X-ray room. And normally, the public doesn't have records of their exposure. So, of course, we have to be better safe than sorry. So if you notice here, the public limit is a lot lower as compared to the occupational limits. So for public, we have 1 millisievert per year, average over a period of 5 years. It may be higher for any single year, but if you average it, it should only fall to a lower or not more than 1 millisievert per year. For occupational exposure, we are permitted, I say we because I'm also a medical physicist and been wearing a badge myself when working in the hospital before. So 20 millisievert per year, a maximum of 50 millisievert any single year. But then again, if you average the exposure over 5 years, you shouldn't be exceeding 20 millisievert per year. So just to put this values in context, right? So let's just look into these three comparisons. So one of the daily activities, or one of the daily objects that we might be very familiar with, which is actually radioactive, is a banana. So a banana, which is potassium, its equivalent dose is 98 nanosievert, and therefore it says that you can have 10,000 bananas per year or eat 27 bananas per day if you're just going to compare your radiation exposure from eating a banana. As a comparison for other occupationally exposed people, such as flight attendants, the annual dose for flight attendants is 1.5 to 1.7 millisievert per year. And for one of the dental procedures that many of us might be familiar with, that is 5 to 10 microsievert per set of dental exposure. Okay, so I hope it kind of gives you an idea on the context of radiation limits. Okay, so now let's talk about risk evaluation. So for risk evaluation, we are actually using these two units of measurement. First is the sievert. So sievert is a measure of the health effect of low levels of ionizing radiation in the human body. The abbreviation for the unit is SV, capital S, small v, and the most familiar unit that we encounter in our measurements is millisievert. 1 sievert is equal to 100 rem. Rem is Röntgen equivalent man, which is an older unit of measurement. We don't really use this much anymore. And for area monitoring of penetrating radiation, for example, the medical X-ray, we use the ambient dose equivalent, which is denoted by H star 10, again given in sievert. And this refers to a dose to a point 10 millimeter under surface of the reference sphere. So this is basically the kind of calibration that is used for instruments that are used to show ambient dose equivalent. So this is used for energy dependent to radiation that have higher penetrating energies. Okay, now let's go back to the X-ray room. So typically, as many of us are aware, these X-ray rooms are lead lined. So you have this lead lining on the walls, and you also see these lead glass windows, lead line doors. And the thickness of the lead that is used for the construction, not only of the walls, but also of the floors and the ceilings, are calculated in the design phase based on the standards. And these thicknesses are given in the lead thickness equivalent of lead thickness equivalent. Yeah, sorry about that. So now, again, when we talk about radiation protection and safety, these shieldings on the walls, on the floor, and on the ceiling would usually give a good measure of safety. But there might still be some radiation that penetrates through this shielding. And this is where the risk assessment comes in. So since we have different limits, if we just go back to the occupational and the public limit, there are areas which are designated as control areas. So these are areas that are only accessible for those people who are in the occupational category and who knows their way around radiation. And this can also be now then we consider how about for other areas that are not designated as control areas. The corridor, changing room, parking lot, which is outside. How do we estimate the time that persons occupying these other spaces can be when we talk about risk assessment? So there is one way, and that is through what we call the occupancy factor. So occupancy factor is defined as the fraction of an 8-hour day, which is 2,000 hours per year, for which a particular area may be occupied by a single individual who is there the longest. So as you can notice here, of course, for the control area, we can see that T, or the occupancy factor, is equal to 1. Similar, for example, for a changing area and for the office where it's usually always occupied. And then for the rest, for example, if we talk about the corridor, occupancy factor falls to just 1/5 of the fraction of an 8-hour day. Lower for, let's say, for example, for the parking lot, which is 40th fraction of that 8-hour day occupancy. So normally over time, very little changes are actually observed on this shieldings, but then some other points of interest could be, for example, lead glass, the door jambs. So it is important to measure if there are any leakage or scatter radiation in these areas. And so that's the next part that we're going to discuss, measuring leakage and scatter. And we're going to start with measuring the leakage. Okay, I hope you are still all with me. It is very challenging with this kind of webinars when we cannot really see each other. But yes, please bear with me. We are now talking about the measurement part. So measuring leakage. How do we measure leakage? So as I mentioned before, there is angular dependence on this type of radiations. So typically, the leakage radiation is measured in 5 directions. So you have the front, the rear, you have the top, and then you have the anode side plus the cathode side. And the distance from the focal spot to where you measure the leakage radiation should be 1 meter. And of course, an instrument is needed. So let's look into that. So in this example, we have the RTI scatter probe, which was recently launched at the RNSA 2020. And it comes in a soft shell case. So in this case, you have the scatter probe with the handle that folds out into a tripod and allows the probe to stand on any suitable flat surface. And the scatter probe has two sensor areas. One is the 100 cm and another one is the 10 cm squared. And we've done this mostly to comply with the existing requirements. So there is also a possibility to mount this scatter probe in any other tripods, such as a camera tripod, as you can see here. And yeah, so that gives you the flexibility whether you want a short tripod that we provide or a tripod that you have on your end. So in preparation for the leakage measurement, so what we do is we place the scatter probe at a 1 meter distance from the focal spot. And then the collimator here is closed. And an exposure is made using appropriate technique settings. You can see here the exposure coming in the display of the scatter probe. And then for the next measurement, the scatter probe is moved to the next position. Again, verify the 1 meter distance from the focal spot. And an exposure is done. You see here the second exposure, and then you repeat the same for the remaining positions. So when all the measurements are collected, then we normalize this for the workload, and there's an equation here that is required, but we will show that later on. And then we compare that to the limits. All right, so now let's proceed into measuring the scatter. Measuring scatter as compared to measuring the leakage is a little bit different. In measuring scatter, to generate the scatter, we use a phantom. It is not good, of course, to use a real patient here. So what we use instead is a 20 centimeter tall PMMA slab. If you don't have PMMA slab, we can also use a water phantom. That would also work. So we see here, the procedure is similar to the leakage, but for scatter measurement, we open the collimator. And another thing here is there is really no defined standard on how far the sensor is to the focal spot, but it might be good to record this distance to source. So if you need it later on to calculate the dose using the inverse square law, you have a good reference of the position. Okay. So an exposure is done, and then you capture the measurement here in the display. Okay. So what else can we do here? We take the scatter probe outside of the room, and then we do a measurement outside the control area, and then we see whether there's a scatter transmission between the glass. We capture the measurement here, and then we go to the other side and also check on that side as well. We do another exposure. So you can notice here that the air therma is relatively lower behind the lead glass as compared to what we have measured inside of the room earlier. Okay, so if we also need to do a sniffing around for leakage and scatter radiation, we can also hold the scatter probe, like what Soren is doing here. And we can use the start and stop button at the back of the probe to do that. Right. So there you have it. The instrument that we were using on those two presentations that we just had for scattering leakage measurements is the scatter probe. So as just a little bit early, this scatter probe has two sensory areas, the 10 cm squared and 100 cm squared, to comply with the requirements. And at the back of the scatter probe, you have the start stop button, and you also have here LED lights that would indicate to you the intensity of the radiation. So this scatter probe actually connects with a USB cable to your laptop or to your tablet, which acts as a display unit. And let me just go through a little bit in detail how does the data from the scatter probe is presented in the software that comes along with it, which is called the Ocean software. It is a Windows-based software, and it is your interface that will guide you and will prompt you for action when a selection is needed. So before you start with your measurement, at least two decisions need to be made. The first choice is that are you going to measure air thermal rate, or are you going to measure ambient dose equivalent rate or mean energy? So what are the differences? In ambient dose equivalent, the unit you get is the sievert, which is often used for scatter measurements. Air thermal rate, you would usually get your measurements in milligray or milliröntgen, which is measurement for leakage. And then if we select mean energy, then that means that we are showing the mean energy in keV of the scattered spectrum, as well as the HPL is presented as well. So just take note that the mean energy keV is the accelerated voltage. It's different from the kVp, which is the kilo voltage peak that you would usually see in the control console of the machine. Okay, so as I said, that's the first decision that you would have to make. The second decision that you would have to make, or the second choice, is the choice between the size of detector that you will be using. Will it be the 10 cm squared, or will it be the larger detector, which is the 100 cm squared? All right. Okay, so let's just have a look into the main view, which we call the quick check. So on this quick check, you have the display of your measurements. First, you have the grid where you have all your parameters displayed. And then, sorry, this is your grid. And then you have here the waveform displayed as well for each of the measurement that you select here. Once you have collected several measurements, you can toggle and click, and it will show you the different waveforms for each measurement. So if you take a look in this measured values, there are some extremely low doses. For example, the 135 nanogray, for which the catapult can still provide a very, very well-defined waveform and a steady measurement. So if you just calculate that back, this nanogray over this measurement time, that is just 8 nanogray per second. So it could be interesting to look at based on the risk assessment that we're talking about. All right, so earlier we also mentioned about the sniffing around for hotspots, and what we used to sniff around is what we call the free run mode. And the free run mode can be done using by clicking the start or stop button at the back of the scatter probe, or you can also use this button here on the right of the display. All All right, so a similar situation here is shown for ambient dose equivalence, only with other units, measurement units. Okay, so it's very interesting to note that different level of radiations can be picked up, but what is also very interesting to see is that in this display software, you can also capture all the very low level radiations in your measurements. So that just shows the sensitivity of the instrument that you're using. So then let's talk a little bit more on how we use this software, so which is what we call the ocean. So there is a possibility to do more than just using this software as a display. So with this ocean software, we have templates provided, and how do we access the templates? So when we're making a new measurement, in the case, for example, we want new leakage measurement, we select new measurement, and then we can choose among already designed templates. So for example, here we select the leakage template, and what we capture here, let's say for example, we have the scatter probe connected to the laptop or to the tablet, and we see this green button, which means we are ready to take measurements. So the exposure time and the exposure detector is collected, and then after this exposure, the scatter probe will calculate these measurements in the template, and the rest are calculated depending on the preset formula. Like for example, here the reference distance to the source is 200 centimeters, and the formula is actually able to give, using inverse square law, the actual exposures at reference distance, which is 1 meter. So you have here 22.41 microgray. And the template will also automatically calculate for you the maximum exposure in 1 hour based on maximum continuous MA. There's also normalization for those in 1 hour given in milligray. And also you have here the comparison based on the limit. So we mentioned earlier that we have to take leakage measurements on several locations. So we just go on through that. Up we see a fail. Why could that be? We'll go back to that. Okay. So one of the reasons there could be a fail here is because we didn't account for the actual distance from the detector to the source, which is actually 75 centimeter instead of 200 centimeters. So if we just make sure that we are using the actual information on the template, we can correct that, and then the fail disappears. So we have the analysis displayed here. So the leakage compliant test is passed, and the result is passed. So there's a possibility right away of converting these values and analysis into a report. And this is just a quick glimpse of what can be done. So on this report, what we have here is leakage distance compensated. You have all the measurements you took, the detail of the test date, the summary of the test, and you can also have here the data, the serial number of the detector that was used. Yeah. All right. So in summary, we're now coming to an end of this presentation, and I hope we were able to share with you a good review of the scattering leakage measurements and how that could be done, and a possible new instrument that measures leakage. And just before we end this presentation, just a few notes. that we would like for you to remember. The scattering leakage measurements, they need to be normalized to workload, occupancy, and distance. So those the leakage and scatter are very low level variations. Thus, it needs some very detector to do the job. So for what we have here, the scatter probe from RTI, this scatter probe has very high sensitivity and it can measure and detect very weak radiation. And since this is a solid state technology, there's no need to compensate for environmental conditions such as the temperature or pressure. So this is really very easy to configure and set up. As you also noticed earlier, it comes in a compact and easy to carry kit, so you can carry it with you anywhere. It is also very easy to mount with the industry standard thread here. You can have versatile setup. You can use the tripod that it is provided with or connect it to a camera tripod. And with this easy mounting options, you don't have the risk to expose yourself when making the measurements. You can just leave it there with the tripod and go outside of the X-ray room. And last but not the least, of course, we have the software that is available to hopefully help improve efficiency, save you some time, and help you improve traceability for your measurements. And for that, that concludes our tracking and scatter and leakage presentations. Thank you very much for your attention. And we are open now for question and answers. For any one of you who are shy to raise your questions during this webinar, you can always contact me. Here's my email address, or you can also reach out to our local partners within your country, and you can find them on the RTI website. Another thing that I would like to mention is some inquiries about being able to get more training about our RTI instruments. You can actually go through our website and go through RTI Academy, where basic trainings are available, and you can also get certificates from those trainings that we have online. So with that, now we are ready for Q&A. I think we have a few questions that came in during this presentation. So let me just make sure that I unmute